All right, so this talk is about control, how to control inferences. That's why it's called bounded rationality. We will work under the AGI assumption that we are just being talked about. So first, I'll try to set up the scene a little bit, then I go briskly to the general ideas. Then I get deep in details. We will see also how the inferencing is based on simulation. And last, I will show you a small example. So there are three things that we desire in engineering. Multi-objective control. It means, in fact, that to achieve a mission, more often than not, a system has to pursue several goals at the same time. There is no option to do one or the other. One has to conduct both at the same time, while, of course, avoiding to violate any sort of constraints that is also imposed in the mission. Note also that those goals can also be antagonistic or overlapping, so we need here a mechanism to make sure that all the goals will be achieved in due time with respect to what is available in terms of resources and knowledge. Next, we also need anticipative control. If a system does not predict or keep its prediction up to date, when it's time to apply its plan, it will lag behind the plant. It means, in fact, that we will act on the state of the world which is not valid anymore. Conversely, since the resources are limited, we just cannot predict everything and anything. We have to make choices. The best prediction to allocate resource to are the ones that pertain to the goal. It means, in fact, that the prediction must be kept up to date, while the goals also are kept up to date. It's a mutual reinforcement, actually, here. Last, we want anytime control. What do I mean by that? Well, it's sort of a standard in engineering term. It means, in fact, that the value of achieving a goal depends on the time. It's not known in advance. It depends on the environment. For example, it's more valuable to make a fuzzy diagnostic before the client dies rather than the perfect solution after the man is in the grave. All right, so what are our predicaments? Fixed memory budget, number of CPUs is fixed, the frequency of the CPU is also fixed. The time to compute a task, well, it depends on the task. So one cannot know beforehand how much time it will take. This is a radical departure for standard control engineering, where all the tasks are known in advance. Their worst execution time is also known in advance. It's just a problem of schedulability. Well, we just cannot make such assumptions here. The knowledge is limited and is insufficient, incomplete, inconsistent. Well, it is experience-based. It comes from learning. The relevancy of knowledge is also dependent on the context and the goals. Last, the knowledge comes and goes. Some skills that have been acquired might prove in the long term not as accurate and might be dropped in favor of new skills. So, unlike standard control engineering, we cannot rely on a firm base of knowledge. The algorithm that the machine will use to perform are not known in advance. Last, we face, as always, a deluge of input, from which we will have to choose those to allocate the resources to. The attention problem. Okay, so now what are the general ideas? All right, so if we have varying knowledge, if we have a lot of inputs, well, logically it produces a deluge of inferences. The question will be which one to perform. We won't have the time to perform them all. Second thing, we face continuous time and asynchronicity. There is no such thing in our view as time steps, or what shall I do next? If the system is ever in the position to ask such a question, the system fails. We have to keep the latencies under control. It means, in fact, that we don't know in advance how many things the machine would have to do, how many inferences in sequence, in parallel. We don't know that. We just cannot assume any sort of cognitive cycle, such as I perceive, I reach the quiescence, then I decide, I don't look at the world anymore, then I act, and my perception, they might be completely irrelevant by now, but I don't care, I'll continue. So we had to abolish this, actually. We have to keep expenditures under control. It means, in fact, that we have to make sure that the most valuable things are actually allocated the time and the resources. And we also have to make choices to discard things. So here, the problem that we face is inverse as what we find in the industry. Here, we are going to strive not to do work, to do the least that we can. It is always opposed to this view, an argument I call the fast enough thing. It's always said, oh, well, you don't need to perform all of those things in parallel. In principle, if the machine is fast enough, then all your inferences can be nicely piped in a single stream. Bon. Reality is completely against that. We don't know in advance what the latencies are. By intertwining streams of inferences, we obligatorily add up and pile up the latencies, which can violate some constraints, which are to be evaluated in the back of the pipe. So, no fast enough argument. Goals and prediction for the anticipatory control must be performed in a concurrent way. And since we target anytime response, we have to pre-compute and to keep pre-computation up to date, to pre-compute plans, I mean. So we have to simulate what-if scenarios and keep those knowledge always up to date, so that when it matters, when the system is asked for an immediate response, then we have at least a few solutions without spending the time to recompute them. Okay, so what is the substrate? What is the knowledge made of? It's made of models, like M there. Okay, a model is like a rule, except that it works in both ways. A entails B, but also in the other one. When I want a B, it's a good idea to chase an A. All right, so those are what we call respectively forward and backward chaining. Each time an inference is made in a forward way, we fork PM there, prediction monitor. What is a prediction monitor? It's another kind of program that is there to check in due time if the prediction comes true or not. And then it tries the model, and if the model performs well, its reliability grows. If it performs badly, its reliability shrinks until death. Last thing, in the backward chaining mode, we also fork a goal monitor. This is used for deciding what to simulate, what to commit to. We will see that in the end of the talk. So this is rather simple. So what the system knows, it's a bunch of those guys here, models. Some are a little bit more complicated. A model like M1, M2, M3 can be preconditions to allow or block the execution of yet another one. So we have here AND arrangement. Notice that AND is actually a weighted AND. It is not like in digital electronics. It's more like in the analog realm, the more evidences of M1, 2, and 3, the more reliable will be the output of M0. Okay? And so this was for the weighted conjunction. We also implement this junction here with the OR. All right? So the entire mind of the system consists of a dynamic network of circuits like this, which are learned. The wiring is indirect, is coupled by data. Double capability, as we have seen, predict and control depending on the way the inferences is made. Functionally speaking, this corresponds actually to a standard negative feedback controller that we find in the computer theory, control theory. Okay, the network is continuous. The quantity and the quality, I mean the reliability of the evidences do matter. It is not one or nothing. It's always in between. The network is also persistent. Once an inference is made, it is refined over time as new evidence or counter-evidence are accumulated. Last, the control that we have over the system is actually the control over the inferencing process in and itself. So it goes at the lowest level, the level of job. The job is just the processing of one input or an inference by a program. Okay? It's pervasive also in the sense that it goes from the top. The top is where the mission is defined, goals and constraints. All of those goals, they trigger cascades of sub-goals that go down to the effectors, and from the bottom up, from the sensors to the prediction on a more abstract level. The structure now of the ABL is like this. We have a set of programs. Programs are models, prediction monitors, and so on. We have a lot of inputs and inferences, and the coupling of those two guys creates a deluge of jobs. Now the question is how to schedule those jobs, or more exactly, not to schedule most of them. Okay. Please note as well that all computation times in the model here are bounded. We have a writer, W, is the process responsible for instantiating jobs, and an eraser that, depending on the value of the data, the program, jobs, inferencing, and whatnot, will kill some of them so as to make room. So, jobs are assigned a priority which depends on time. It depends on time and a few things. First, the tending value of an input or an inference. It is, in fact, the quality and the length of the inference chain that produces such an input. It decreases with the time horizon. It means, in fact, that the more close a deadline is, the more important the input is. With the exception of goals. In the case of goals, when the system can predict that the goal state might be achieved by other means than pursuing that goal, well, the priority of that goal will get lower. It is one example where the goals and prediction inform each other. And the relevance of a program actually is it is in the context. So for the program, its relevance is defined as the best tending value of its goals and its predictions. It means, in fact, in the current operation, what are the most active piece of code? The eraser, as I said, is based also on value, on the same thing, the tending value, the relevancy. And it is also based on prediction. So it means, in fact, that periodically the eraser will predict the resource expenditures and make room for new inputs, new knowledge. In our case, you see there is no dedicated attention mechanism. The attention is, in fact, the job priority. It boils down to a mere scheduling problem. So simulation, we simulate continually the possible outcomes of goals so as to pre-cook plans, and when the time comes, we just commit to the best solutions. Notice that commitment is revisable. We might, a system might, for example, commit to a course of action. It unrolls it, the situation unfolds, it might change its mind and switch to yet another plan, which was still in simulation mode. How it works is simple, actually. Here, a hierarchy of goals, from the top level goal G0 to some terminal goals like G4, for example. Each time a goal is created with a prediction that simulates what if this goal was succeeding. This is food for the other goals that we can see on the right side, G5 and G6. In fact, it means that all the monitors of the goal will accumulate some simulated outcomes so that when they are asked if they should be committed to or not, they can compare the relative importance to some other goals. For example, a goal, the outcome of which would block or prevent the achievement of a more important goal will decline commitment. But this is revisable as new evidences are accumulated. So that's why I say the commitment is revisable. When do we commit? We commit at the earliest of the earliest deadlines of goals. It means, in fact, that it's the deadlines of the effectors. So we have applied that in a concrete case. It was about a real-time interview with humans, actually. So using this model, the machine could actually act in a multi-modal way, coordination of speech, pointing, nodding, listening, and you name it, all in parallel and in synchronization. Anticipation was demonstrated on the full scale of the interview. So the synchronization of word utterances was carried from the word itself, the sentence, a block of sentence, up to the interview, 5 or 6 minutes to give you an idea. The system was continually predicting the behavior of the human so as to detect some opportunities, like to speak without overlapping, and also to predict any sort of mishaps, like overshooting the deadline of the interview. Yeah. So, yes, so the main idea in here is, A, the knowledge is variable. The resources are completely fixed, and we have to keep the system on its toes. To do that, we have to inform the goals with a concurrent flow of predictions. There is no way those two things can be put in sequential streams. I guess that's the main idea to take away. Thank you. Thank you.